This video is going over the layers of the Earth as we hypothesize them to be at this moment. And this picture here shows us a pretty good summary of what those layers are. The outer layer here that we know of is the one that we interact with all the time. It's the crust, and as you can see, it's really thin compared to the thickness of the other layers of the Earth. It's anywhere between 7 to 50 kilometers thick at most points, and thickest parts of the crust are the continents, the ones that rise above the ocean. These are the really thick parts, and the thinner parts are covered with water on top because they're so thin and dense, and they are the oceanic crusts. Underneath that, we have this really thick area of semi-molten magma and rock, which is called the mantle. Then we have an internal area here which we call the core, the inner and the outer core. And here you can see those three main layers, the crust, the mantle and the core. And it's got their relative thicknesses here. It's saying here that the crust goes up to 100 kilometers thick at its biggest point. The mantle, in comparison, is almost 3,000 kilometers thick, and the core is 6,800 in diameter. So if you think thickness to the middle of it, it's about 3,400 kilometers thick. Now, because things that are more dense and heavy tend to sink, the heaviest and densest elements are actually in the core here. The lighter ones are in the mantle, and then of course we have the crust, which is basically solidified mantle on the top. The mantle is semi-molten rock, but when you expose it to air or to space or to water, of course that rock's going to cool down and solidify, and essentially that's how we make the crust. Now, to think of these layers, you can also think of it like a cake here, with the core and the outer layer, the mantle and the crust on the top. We're going to use these notes now to help fill in this PDF that you've been given on the different layers of the Earth. There are different layers that we're going to be talking about, and we're going to focus firstly on the crust here. If you look at the crust up close, there are actually two components to it. There's an oceanic crust and a continental crust, and essentially these form where we find the oceans and the lands. The oceanic crust is a lot denser than the continental crust, but because this one's actually thicker but slightly less dense, and because of that, this one tends to sink a little bit lower into the mantle here and be pulled under the continental crusts. Here's another coloured version of that picture, and as you can see here, we've got the oceanic crust and the continental crust, which are basically the solidified rock from the mantle below. And you can see the thickness of the land here compared to the thinness of this ocean crust. So of course the water's all going to go down this way and form oceans. And you can see here that this oceanic crust is actually dipping below the continental crust. Because it's a little bit more dense and heavy, it tends to drop down that little bit more, which means it tends to be forced under the continental crusts. And here's a pretty good example to get your head around how thick this crust really is. If it was the same size of an apple, the skin on that apple is essentially equivalent to the thickness of the crust around the Earth. It is really thin compared to the vast majority of the interior of the Earth. Next, we're going to look at the mantle. Now, this is the next part of the just underneath the crust here, and you can see that it has these funny little symbols here with the name convection currents. Now, that's because we are pretty sure that the mantle itself, especially in the middle there, tends to move around. When we know that because the crust on top is moving around, something must be pushing it. And it's certainly not the wind and the rain above the crust that's pushing large sections of land around the globe. It has to be the convection currents or the movement of the mantle underneath that pushes the crust that sits on top of it. Now, you can see convection currents in everyday life. If you have even water boiling, you'll notice that where the water is close to the flame, it tends to rise up, and then when it gets to the top and cools down, it tends to go down. And this forces a current, a circular current like this, where particles are moved from hot upwards, and then when they get cold they move downwards. Now these convection currents work then to churn up the mantle and move whatever is on top of it around. Now the mantle again is broken up into two sections, the upper and the lower. Now the upper mantle we don't think has an awful lot of convection currents. We think they actually form in the middle here. And although I say that this is moving, realize this is a semi-solid mass that is still very sludgily moving around over a very long period of time. Lastly, we're going to look at the core. Now this is the outer and the inner core, and this is the area of the Earth that we think is made up of the heaviest and the densest elements that form the Earth itself. Remember, things that are heavy and dense tend to sink, and things that are lighter tend to float. So we hypothesize that the heaviest elements of the Earth, most of them are found within the inner core and the outer core. Now here we've got the outer core. We think that it's liquid, and again, as you will see on the evidence video, that's because of the way that earthquake waves do or don't travel through this section of the Earth. And we think it's mainly composed of heavy metals like nickel and iron. Then we have the inner core. We think that this is mostly iron because of the magnetic field that's been generated around the Earth. We also think it has to be solid. Okay, it's believed to be up to over 6,500 degrees Celsius. Now we're also sure that there must be some radioactive elements down in here. This is based on the amount of heat that is generated down here. We believe it had to have been generated using radioactive decay, and also from some of the elements that rise from deep within the Earth's crust, having some radioactive particles to it. Now, just to confuse you more, scientists have actually broken these parts up into other names and sections as well to describe how we interact them. Now, we call this lithosphere here the crust and the upper section of the mantle that we can sometimes interact with here. The next section down we have is the asthenosphere. Now this is the layers of the mantle that are really hot rock and tar and move slowly around with those convection currents. Then we go back into the names of the mantle, the outer core and the inner core. And here's another picture here of how the lithosphere and the asthenosphere interact. The lithosphere is basically the crust and the very top of the mantle, which doesn't tend to have convection currents in it, so it's not really moving. And the asthenosphere is the part that has those convection currents. It's the semi-solid rock that's moving around and around. And as you can see, some of that liquid magma has pushed up here, and this is actually coming out in the ocean there to form new land. This is where some of that magma actually escapes under the ocean. So the asthenosphere is that soft layer of the mantle that moves around, and the lithosphere is the part of the mantle that's pretty solid and actually sits on top of it. Now here's a fantastic picture of that. We've got the lithosphere, which is our crust, plus that upper solid part of the mantle, and we know that they're divided into little plates. Now if the asthenosphere, this moving part here, is moving around in currents, it's easy to picture in your head that if this is moving around like this underneath, that it's going to be pulling the crust and the mantle apart, the things that are sitting on top of it. So this sort of current here either pulls continents apart or pushes them together. And this sort of movement is how we think continents have moved around the globe over time. It's also the reason we have things like earthquakes, and also how new land is formed and destroyed. So as these guys here are pulled apart, magma will come up between the cracks here and form new crust here. And this actually happens in the oceans as the land is pulled apart. We can see this from space. But on the other side, you've got land that's being pushed together. And as they get pushed together, one piece will either dive down underneath it and get destroyed, or they'll both push up into mountains moving together.